Alrighty, we are working on section 9.1. Alright, you may or may not be watching this on Monday, so I'm going to change this to happy day. Woo! Alright, but section 9.1 is all about translations, and we're getting into a chapter about different transformations on the coordinate plane or just in two-dimensional space. So our goals for today are I can identify rigid motions. So what in the world are rigid motions? And I can find translation images of figures. So we're going to work on one of the transformations, which is translations. So now to get some background information here. This is actually at the beginning of the notes that are given to you, I believe. Um, but we've got some things we gotta talk about before we can get into all this stuff about translation. So first of all, let's just read through some of this background information. It says a blank of a geometric figure is a function or mapping that results in a change of position, shape, or size of the figure. And that would be a transformation. That's what we're talking about, transformation. All right, and hopefully you can read that. Move that back over there. Transformation. All right, next. The original figure of a transformation is actually called a pre-image. And the final figure, the one that you end up with, is called the image. Okay, so it's pre-image and image, not image and post-image or original and final. Really, they're called pre-image and image, just so you're aware. In other words, a transformation is any movement of one figure onto a similar figure. So, a couple notes. The book, if you're doing, the book will always have the pre-image in black and the image in blue if you're dealing with the book. We're not going to be able to tell so much on our notes. Um, so usually, the image is usually gray then. All right? But let's look. It also says the pre-image will be a thin line, the image will be a dotted line, the final image will be a solid dark line. So there could be a middle one. So an image would be a solid. That would be the final image will be a dark solid line. All right, there are four types of transformations that we're going to deal with in this chapter. Translations, which you can see a picture there. It's just kind of sliding things over. We'll talk about those more today. Reflections, which are just flipping over a line. Rotations, which are rotating around a point. And then a dilation, which is an enlargement or reduction, so making something bigger or smaller, which we've kind of dealt with when we've talked about scale factors and proportional things. So we're just going to do a little bit more with that, see some different notations for those. All right, one final thing that I'd like to note here. If the resulting image is the same size and shape, meaning that would be work for all the first three, translations, reflections, and rotations all end up being the same size and shape, then that is called a rigid motion. So it's said to be rigid. I want you to know what this term is because you'll be using this term this chapter. If the size changes like a dilation, the transformation is said to be not rigid. I don't know if there's a fancy term for it. We're just going to say not rigid or not rigid motion. All right. So let's go on and let's find some examples of rigid or not rigid. So example one: does the transformation appear to be rigid motion? This one I'm going to say yes because it has the same size and shape. B, I'm also going to say yes because it has the same size. You know what? This is actually a no. This one would not be a rigid motion, simply because it does not have the same size. So it has to have the same size and shape. In other words, we're looking for congruent things between the pre-image and the image. They can just be in different spots. All right, a transformation maps every point. Here's something to note. A transformation maps every point of a figure onto its image, and maybe you're described with arrow notation. So we have according to this, they're red, probably just dotted on yours. Prime notation, just so you know, when you have an image, you start with just regular letters. JKQ would be our pre-image. And then when we map over to our image, the letters have this little apostrophe on it, which would be a prime notation. So we're just our image is JKQ, or sorry, our preimage is, and our image would be J prime, K prime, Q prime. So we always add a prime to say that that's our second one. If it's if it's mapping onto another image, it'd be the third one would be J double prime. So there'd just be two apostrophes by each of those. So that's just a notation thing. You're going to need to really know the notation for these in this chapter. All right, and I have one more example here. In the diagram, NID goes to triangle NID maps onto triangle SUP. What are the images of um, angle I? And actually, order matters again. So it would be angle U, and angle D would then go with angle P, just like when we talked about congruent and similar triangles. And corresponding sides would be also here as well. So we'd have um, NI and SU. We'd have ID and UP. And then we'd have DN or ND would go with PS. All right, so that's some background on rigid motions and transformations. So let's focus on this first one just a little bit here with translations. So transitioning to what translations are. A translation is a transformation that maps all points of a figure the same distance in the same direction. So we're just sliding the whole figure, not turning it at all, not flipping it, not rotating it, just sliding it. So we're going to put that right here, sliding it. You write the translation image of triangle ABC onto triangle A prime, B prime, C prime. We just talked about those. As we can write it this way. Here's one way to write it. T with the translation, that would be translation capital T, in parentheses, triangle ABC, and then it would end up equaling triangle A prime, B prime, C prime. It is a rigid motion, and they have the following properties. So all the side lengths are congruent. Or actually, you know what, this is not the side lengths, this is the distances between the points. So B to B prime would be the same as A to A prime, would be the same as C to C prime. Those are all the same. They're all parts are moving the same distance. There's no difference in those. Second one, so that was the first one. Second one, AB is equal to A prime B prime. So that's where, I'll use blue for this one, the side lengths are going to be congruent because they're congruent fingers. And then the angles, the corresponding angles are going to be congruent as well. So that's our last one. So we have angle A would be congruent to angle A prime, and so forth. Now, notation. We showed you one notation to write it. This is actually a more common notation for writing a translation. It gives you a lot more specifics. So, no, this is important. I wrote notation 3 times because we're going to have different notations for all 4 types of transformation. So for the fixed values A, B, or A and B, a translation moves every point. So this is when we're looking at a coordinate plane. We're transferring on translating something on a coordinate plane. It moves from the point xy to the point x plus a and y plus b. So you're just adding whatever it is. And actually, yeah. So, in other words, this is our notation. We're saying it's a translation. So we're taking a point or a figure. We're translating movement on the x-axis. So this is not an x value. This is how far you're moving it to the right or to the left. Okay? Take note of that. And the y would be the how far you're writing it or moving it up and down. So positives would be up, negatives would be down. And we're using these little triangle brackets, these little arrow brackets. All right? And those are also a subscript, so smaller letters. Then then at the end we're putting what it is that we're translating that many places. So this is the figure RSTU. All right? So let's put this into action a little bit with a few examples. Example 3 says, what are the vertices of, so this means we're going to move it right 1. So the translation, right? I totally spelled that wrong. 1. And if it's negative 4, that means we're going to go down 4 of this triangle ABC. So this is a translation again. So we're going to move it, each point, we're going to move right 1 and down 4. 1, and down 1, 2, 3, 4. So there's A prime. B, we're going to move right 1 and down 4. 1, 2, 3, 4. So there's B prime. And then finally C, we're going to do right 1 and down 1, 2. We have to make our own lines here. 3, 4. And that would be C prime. And then you draw your triangle for C prime. It should be exactly congruent. Now mine's not perfect because I'm not a perfect artist. But you can see it didn't move the orientation of it. It's still, the A is the upper right or upper left point. The B is the upper right point, and the C is the bottom point. It's just sliding the whole figure right 1 and down 4. All right, so let's go backwards now. Let's say example 4. What is a rule that describes the translation that maps PQRS to P prime Q prime R prime S prime? So we're going backwards. We have the translated figure, and we need to write the rule, so the notation. So I'm going to start with a T, and I'm going to use my little arrow brackets. And the thing that was translated was P, Q, R, S. Now we just have to figure out how it was translated. So let's look right here. The first number is how many right or left. So it looks like it's going right. 1, 2, 3, 4, 5, 6, 7, 8. So 8 to the right. And down 2 says -2. And you can check each one. They should all be, if we're saying it's a translation, they have to all be the same. So like I could check this one. 1, 2, 3, 4, 5, 6, 7, 8, and down 2. It works the same for all of them. 1, 2, 3, 4, 5, 6, 7, 8, and down 2. 1, 2, 3, 4, 5, 6, 7, 8, and down 2. So they're all right 8 and down 2. So that's a good translation. That would be our rule. All right, let's look at one example here. The diagram shows two moves of the black bishop in a chess game. So I don't know if you know how to play chess. I'm really bad at it. But a chess game, the bishop next moves 3 squares left and 3 squares down. Okay, so it moves from here to here, from here to here, and then it goes 3 squares left. 1, 2, 3, and 3 squares down. 1, 2, 3. So the bishop is now right here, and I should probably draw that in black. This is where our bishop now is. And we want to write well, it says, where is the bishop in relation to its original position? So let's actually write it as the notation. So I'm going to say it's a translation of, well, we'll do this. I'll figure out what those are. And we're just translating the bishop this time. Nothing too fancy. It's just the bishop. So how far did it go to the right? 1, 2, 3 to the right. And then it went down 1, 2, 3, 4, 5. So that'd be -5. I feel like it's always going right and down, but there'll be examples where it's not. So that would be it. Went right 3 and down 5 ultimately. But really it went there, 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 and there. All right, and that's the last one I really wanted to do. You can take a look at this one. And think about this. It says graph a figure triangle ABC and reflect it over the line x equals 2. Okay, so we haven't done reflections yet. Then reflect it over the line x equals -2. So let's see if you can do that. It's not something that's required. We're going to get to that, but I'd like you to try it. Just see how you do with reflecting over those lines, because that's going to get us into, I think our next section is on reflections. All right, and then please answer the closing questions. What is a transformation that preserves distance and angle measures? What's that called? We said it a little bit differently. Same shape and same size right there. And how can you write a rule for a translation? Describing that. And then please answer the final error analysis questions as well. All right. All right, that is all from section, well, introduction to our chapter, and also section 9.1. Go back and look at these two goals. I can identify rigid motions, and I can translate images of figures. All right, we'll see you next time.